Welcome to this lecture. In this lecture we will talk about reactive ion etching and deep reactive ion etching. Now if you recall a bit, we have already seen how wet etching can be used. What is the use of etching? The use of etching is to etch different materials, or we can say etch materials from the unwanted region. We can use chemical. If you use chemical, it is called chemical etching or wet etching. If we use different kind of gas, then we call is as a dry etching. So, reactive ion etching and deep reactive ion etching are both dry etching processes. In RI you use chlorine based etcher or fluorine based etcher. In DRI generally is used to create a high aspect ratio features, that means you etch silicon wafer all the way either through etch or all the way to create a diaphragm as thin as 1 micron. So, we will see how these techniques are used. Just to give an example, if you see the slide, so we will talk about RI and DRI. I will give an example of what we are talking. So, if you take a silicon wafer, perform a photolithography technique, that means that you know now that we cannot directly start using silicon wafer and deposit material, right, because silicon is a semiconductor. So, I have to first either grow or deposit my silicon dioxide or a insulating material. So, here let us say that we have SiO2, this is a silicon wafer and this is also silicon wafer. If we say 4 inch silicon wafer about 450 microns thick, we can use single side silicon wafer, single side polysilicon wafer or double side polysilicon wafer, what we call as SSP or DSP. Now, on this suppose I want to create a diaphragm, then what I will do? I will spin coat photoresist, right, I will spin coat photoresist, and then after spin coating photoresist I can go for soft bake. So, let us assume that we are using positive photoresist, I go for soft bake. After soft bake I load the mask. Now, I am showing in this back side of the wafer, right, you can always flip the wafer and understand what exactly things are going on. If I use positive photoresist and if I use dark field mask, so dark field mask means the field is dark, the pattern is bright, is called dark field mask. So, if you are using 4 inch wafer, you have to go for 5 inch mask. So, this is our 5 inch mask and we are using dark field. We will expose the photoresist after the soft bake is done. Soft bake is generally performed at 90 degrees centigrade 1 minute on hot plate, right. But it also depends on the data sheet and what kind of photoresist you use. So, you can always refer to the data sheet before you optimize your photoresist. Important point while you utilize the laboratory is that the relative humidity and the temperature of the lab is very important. If the humidity little bit high, you can always heat the wafer before processing it to remove any moisture that may be there on the wafer. Now, what we have here is the mask. What kind of mask? Dark field mask, dark field mask, and once you perform soft bake, you can expose this using ultraviolet light. So, UV light exposure, okay, UV light exposure. After you expose in UV light, now what we have learned in lithography, that whatever the pattern is there on the mask, same pattern will come onto the wafer if we go for positive photoresist, or the exposed area will be weaker and the unexposed area will be stronger, or the unexposed area will be stronger and exposed area will be weaker. Different ways of writing the same things, right. The easiest way is whatever the feature size, whatever the features are there onto the mask, same feature will get onto the wafer if we go for positive photoresist. So, after this, what is the next step? You develop it, right. So, if I develop this wafer, develop what? Develop the photoresist. So, when you develop the photoresist, what will happen? We will get wafer which looks like this: silicon dioxide, silicon dioxide, and when we develop the photoresist, you will see that you will have photoresist in these two places, right. Easy, because same features which are there on the mask will transfer to the wafer. So, silicon dioxide is thermally grown silicon dioxide about 1 micron, and for devices, for biosensors or for MEMS based devices, generally we go for wet oxidation. Wet oxidation is faster compared to dry oxidation. This is our photoresist. After this we need to perform hard bake. Before hard bake, I will protect the other side also with photoresist. So, I will spin coat photoresist on the other side and then perform hard bake. The reason of spin coating the other side and protecting it was for protecting the silicon dioxide, right. So, now after this technique, after hard bake is done at 120 degree centigrade 1 minute on hot plate. Okay. So, once you do that, then if I dip this wafer in BHF, buffer hydrofluoric acid, if I dip the wafer in BHF, what will happen? I will have my silicon dioxide etch from the area which was not protected by photoresist. Silicon dioxide getting etched from the area which was not protected by the photoresist. The area which was protected by the photoresist will not get etch. So, this is my positive photoresist, this is silicon dioxide, this is positive photoresist, this is silicon dioxide, this is positive photoresist, this one is silicon dioxide. Okay. And you can see here, now we can see silicon, is not it? We have seen silicon. So, if I see this is the first step, this is second step, this is third step, and this one is our fourth step. Okay. After this, if I dip this wafer in acetone, what will I have? I will have wafer which will look like this. So, this is my fifth step. Fifth step, what I have? I have silicon dioxide in front, I have silicon dioxide in back of the wafer, and here silicon is exposed. Now, if I want to create a diaphragm, so I want to etch silicon, I can either use wet etching technique, wet etch, or dry etch, and today we are learning dry etching. When we go for dry etch, what you will have is if I keep on etching all the way, right, you will have this one. Now, why we stopped here, right? Why we stopped here? Because silicon dioxide will work as a etch stop for any silicon etchant, right. So, silicon etchant cannot etch silicon dioxide, that is why it is somewhere here we have the etching will get stopped. This is what we get by using the dry etching process. If we used wet etching process instead of dry etching process, what kind of wafer we would have? We will have wafer which will look little bit like this. Okay. Now, I am not etching all the way, let us say here silicon dioxide is there. Here what you see is there is an angle that is created which is 54.7 degree. Here also we have created a diaphragm, that means we have etched silicon but using chemical. What chemicals are used for etching silicon? We can use tetramethyl ammonium hydroxide, we can use potassium hydroxide to etch silicon to create a diaphragm. Here we are using DRIE technique, deep reactive ion etching technique, DRIE, to create a diaphragm, right. So, either case 5 or 6 we will get 5 or 6 we will get the diaphragm. So, let us focus on how DRI or dry etching technique works. Okay. So, this is a kind of an example before we actually understand how dry etching can be used. So, you can see here we can get different kind of diaphragms using either the wet etching or dry etching processes. The etching is used to remove the material which are unwanted, and we can use either surface etching or we can use release etching. What is release etching? Release etching is where we can use sacrificial layer. Let me give an example of sacrificial layer. So, I am drawing here. You have a silicon substrate, oxidized silicon substrate, and on this oxidized silicon substrate you have patterned zinc oxide. You have patterned zinc oxide. How? Like this. Okay. So, this is your zinc oxide, this is SiO2, this is silicon SiO2, and this is your zinc oxide which is patterned. On this zinc oxide we are depositing a metal. Okay. We are depositing, let us say, gold. Okay. Now, if I dip this wafer, in ZNO etchant, what will I have? I will have oxidized silicon substrate, with AU micro cantilever, with AU micro cantilever. Here we have used ZNO as a releasing material or sacrificial layer, alright. That is what we call as a release etch. Surface etch is very simple. From the surface whatever you are etching is surface etch. For example, if you take a substrate and let us say you have oxide and you are etching oxide from the surface, right. This is your surface etch, is very simple. You take an oxidized silicon wafer and then you etch oxide from the area which I am showing it here, that is from here, this is your surface etch, simple. So, surface etch for microsystem is used, which is similar to integrated circuits. You can remove the selected region one layer of the wafer to create either a structural pattern or to expose the underlying layer of the material. What does it mean? If I etch silicon dioxide, I can now expose silicon, right, that is what it means. For ICs, the underlying layer is for conductive interconnects. For mechanical components, surface layer is patterned with specific shapes such as cantilevers, mirrors or probes. We have taken an example of cantilever. Release edge is to release mechanical component. Etch is used to remove whatever material is necessary to allow the component to operate according to the design. The component may be required to move upside down or side to side or rotate or vibrate or bend or flex, and this is one of the example of a spring that is created which looks like a leaf spring. The image is a courtesy of Khalil Najafi, University of Michigan, who took the SEM image of this leaf spring. This leaf spring will expand and contracts above the substrate. Okay. So, now what are the factors that affects the etching quality? Etch rate, the rate at which material is removed, and second is directional. So, since etch can occur in all direction, it is important to be able to control the direction of etch. Directional control results in achieving desired shape or etch profile. The direction depends on whether it is isotropic etching or anisotropic etching or combination of both. Selectivity is also very important. That means that the material that we want to etch should get etched, and the material which we do not want to etch should not get etched, or in other way is that it is a ratio of etch rate of material to be etched by the etch rate of material not to be etched. So, what is an example of that? Suppose we create we want to create a silicon diaphragm, right, and we etch silicon dioxide. Again I am taking same example, so it is easy for you to recall. So, you take silicon dioxide here, you take silicon dioxide here, and now you start etching. Okay, you start etching what? Etching silicon. So, if I start etching silicon, what should happen? Only my silicon should get etched and not silicon dioxide, right. So, only silicon should get etched and not silicon dioxide. So, I start etching. You see that when I etch all the way to silicon dioxide, this silicon is all the way to silicon dioxide, that is here, this one, right. The silicon dioxide here in other region, right, is not etching. That means the etching rate of silicon dioxide is way lower than the etching of silicon. That is, in this way is called selectivity. Etching rate of material to be etched, that is silicon, should be extremely high compared to etch rate of material not to be etched, right, which is silicon dioxide. Got it? So, this is how the factors affecting etching quality: etch rate, directional control, and selectivity. Okay. Further, let us understand the dry etch process, and in dry etch process the wafer is exposed to gaseous etchant suspended in radio frequency energized plasma. You can see here. In this particular case, there is a upper electrode, there is a bottom electrode, the wafer is placed on the lower electrode, there are ions, electrons and free radical. The collisions between the gas molecules and energized electrons create a soup of electrons, ions and radicals, right, and this will ultimately etch the substrate or the material on the substrate. Now, if you see dry etching by design, dry etching methods provides much more control over wet etching. Why we say so? So, let me draw it here for you. So, if you use wet etching, then you have this kind of etching, right, but if you use dry etching, what you will have is much more directional control compared to wet etching. This is wet, this is dry etching. That was it means by directional control of the etch, anisotropic profiles, and process parameter which will control the etching are pressure, temperature, gas flow and power. Physical etch is when very similar to sputtering deposition process, it is entirely physical, no chemical reaction occurs. That means that if I include the argon gas for example, right, and then in the plasma what will happen is it will dislodge the silicon nitride material which you can see here, right, from the substrate, which substrate is let us say silicon. In this case we are just bombarding the ions onto the material that we want to etch, and the atoms from the material gets dislodged and thus the material is etched. So, it is similar to sputtering process, but in this case we are not depositing anything, but we are etching it, right. So, physical etch is referred to as ion beam etching, sputtering or ion milling. Ions bombards the surface of the wafer causing molecules to sputter off the surface. Dry physical etch, dry chemical etch and the chemical dry etch process. These are three different things. So, the first one, let us focus on that, dry physical etch. So, wafers are placed onto a negatively grounded holder in a vacuum chamber. Again it is very important to have a vacuum chamber. Also you will see that the substrate holder is tilted, right, with certain angle, so as to have a uniform etching of the chemicals or the chemical reacting uniformly across the substrate. A gas is introduced, the chamber pressure is reduced and RF is turned on, a plasma is generated, gas molecules enter the plasma, collide with high energy electrons resulting in positive ions, and these ions are attracted towards the negative grounded wafer. These ions accelerate as they move towards the wafer, heats the wafer and sputters the molecule from the surface. The process continues until the pattern is etched, expose the underlying layer, or how much etching we need to get it, we can control the etching accordingly. So, but when you talk about dry chemical etch, it's little bit different than dry physical etch. In dry chemical etch, the chemical etching requires the presence of plasma energy and a select gas to etch the wafer surface layer. The process begins as the same as physical etch, but here a plasma is stuck and collisions occur between high energy electrons and gas molecules. However, in dry chemical etch, the radicals formed by collisions perform etch rather than the positive ions. So, when you introduce the gas, then the radicals which are formed will etch the material on the wafer or wafer itself. In physical etch, the gas that you introduce will etch itself, because it will convert into ions, and these ions are converted or used for etching the material. When we talk about chemical dry etch process, it is little bit different, because here the radicals generate faster and survive longer than ions. More radicals are available in the plasma. Radical transfers towards the wafer and are absorbed on the surface, and that which for the material that needs to be etched. In this case, again we have taken silicon nitride as an example. A chemical reaction occurs between atoms of materials and radicals, and the byproducts of this reaction dissolve from the surface and diffuse in the gas present in the chamber. The reaction desorption in this case is a chemical etch. Now, dry chemical etch process, there are two different critical parameters. First is pressure and second is how much power you apply. This is radio frequency. Chemical etching requires high range pressures and low range RF power levels. Physical etching requires low range pressures and high range RF power. So, that you need to understand, if there is a question that what would chemical etch require compared to physical etch, you can easily identify what is the difference. That in chemical etch high range pressure, in physical range lower range pressure, in chemical etch low range RF power levels, in physical etch high range RF power levels. Reactive ion etching, which we call as RIE, uses mid level RF power and mid range pressure to combine both physical and chemical etching. The positive ions from the plasma bombard the surface, at the same time the radical adsorbs to the surface. So, combination of this will etch the material. The RIE process provides high selectivity ratio. Chemical, it also provides anisotropic etching or features less than 3 microns wide. Its ability to capitalize on the advantages of both physical and chemical makes RIE an invaluable tool in manufacturing of microsystems. We can use RIE for with chlorine, and we use RIE with fluorine. This is our homework to identify when we use chlorine and when we use fluorine for reactive ion etching. Now we go one step further, where we want to have features, as you can see here, whether it is a lift spring or whether it is a cavity that is created into the silicon, or there are many cavities of different dimensions that we want to create in silicon. We use a process called deep reactive ion etching, is also called a Bosch process. So, in adding to creating cavities, DRI can be used to create tall objects of components of microsystem devices, which can be released through other etch methods. The SEM of on this particular slide, this one shows the leaf spring created using DRI. This is another example where we are creating a cavity into the silicon. You can see side walls are very smooth, right, compared to wet etching. Most of the system uses Bosch process, that is why it is also called Bosch etching or the Bosch process, where a fluor polymer to passivate the etching of side walls, and the passivation protects the side walls from being etched, but not the horizontal surfaces. During the entire etch process, the gas mixture switches back to forth and between etchant gases and passivation. What happens is, initially when you take the silicon wafer that you want to etch, let us say this is a silicon wafer, right, and initially when the etchant will come, it will start etching. So, it will start etching like this, and once it is etched, you stop the etchant and start the passivation layer. So, passivation, and this is etchant. So, you start the passivation layer, it will form a layer like this, then you start etching and stop the passivation, then again start passivation, stop etching, again start etching, stop passivation. This way you can go all the way to your etching parameter, or the cavity that you want to create, the final diaphragm that you want to have. You can create controlled by using the etching and passivation. The role of passivation is to protect the side walls, right, and that is why you have the features what you can see in this particular slides. And if you just Google DRI techniques and SEM images, you will find many more features like this what you can see on this particular slide. So, the deep reactive and etching, a special subclass of RIE is also used to create deep cavities in substrate. It has a very relatively very high aspect ratios such as 50:1. These cavities can be of hundreds of micron deep while only a few microns wide. You can see in this case is about 20, 40, 80 almost 100 microns depth, right, why only looks like only like 2 microns or 3 microns width. DRI, the SEM image here shows a series of such kind of cavities that can be used in one go. You can notice that the deeper cavities have wider openings. This means that on the same wafer with a number of different etch openings, different widths will achieve different depths, right. Bigger width, more depth, smaller width, less depth. The process, as I told you, is also called as a Bosch process. So, in summary, what we have seen is the macro fabrication technique or any sensor fabrication technique where we are going to miniaturize it and where it is going to use macro technology. Then we have to go for and we have to go for several techniques. First is deposition, then lithography, then etching. When you talk about etching, either it can be wet etching, which can be isotopic or anisotropic, or it can be dry etching, which can be physical, chemical, or both. And finally, there can be RIE and there can be DRI. So, with this we are at the end of this particular lecture where we talk about dry etching techniques. I hope you understand what we are looking into. This is almost your end of the course, right, because we are almost around 9th to 11th the module. And if you are stuck with any kind of question, always you feel free to ask us through the NPTEL forum and we will be able to reply to your query as soon as we can. Right. Till then, you take care, enjoy the remaining lab videos, lecture videos, and I look forward to receiving any feedback or if you are stuck, then any kind of queries. Till then, you take care. I will see you in next class. Bye for now.